Welcome to this lesson on scientific data collection. Today we're going to learn how to collect data systematically and honestly, which is the foundation of good experimental science. First, let's understand what data collection actually means in science. Data collection is the systematic process of gathering and measuring information on variables of interest. It allows you to answer research questions, test hypotheses, and evaluate outcomes. Why do we need to be systematic? Because random, careless data collection leads to unreliable results that nobody can trust or reproduce. Let me show you the first essential tool, the pre-designed data table. Before you even start your experiment, you should have your table ready. Here's what a good data table looks like. Notice it has columns for trial number, your measurements, calculated values, and a notes column. You prepare this before you start collecting data. Why design the table first? Because it forces you to think about what you're measuring, what units you'll use, and what calculations you'll need to perform. During the experiment, when things get hectic, the pre-designed table keeps you organized. You know exactly where to write each measurement. Let me show you a real example. Let's say you're measuring the density of different metal samples. Density equals mass divided by volume. The equation for density is ρHO equals mass divided by volume. Rho is the Greek letter commonly used for density. Let's collect data for 5 aluminum samples. We'll measure mass and volume for each sample. Notice that trial 4 has a density of 2.38, which is noticeably different from the others. This is what we call an anomaly. The question is, what do you do with this value? Here's a critical rule in science. Never delete unexpected data. This is extremely important. That unexpected value might be telling you something important. Maybe there was an air bubble in trial 4. Maybe the sample was different. Maybe you made a measurement error. You record everything you measure and note the anomaly. Don't erase it. Don't pretend it didn't happen. Write it down and add a note explaining what might have caused it. See how we added a note explaining the anomaly? This is honest data collection. You're showing that you observed something unusual and you're documenting what you saw. Think of data collection like a crime scene investigation. Would a detective ignore evidence just because it doesn't fit their theory? No! They document everything and try to understand what it means. Let me expand on this analogy, because it's really helpful for understanding proper data collection. Imagine a crime scene. A good detective places markers at every piece of evidence, even the ones that seem unimportant. Why? Because later analysis might reveal their significance. A bad detective ignores evidence that doesn't fit their initial theory. This leads to wrong conclusions and miscarriages of justice. A good detective documents everything systematically, takes photos, makes notes, and preserves all evidence. They let the evidence guide their conclusions. Your experimental data is evidence about how nature works. Treat it with the same respect and honesty that a detective treats crime scene evidence. Now, let's address something really important. The pressure to get perfect results. Many students feel pressure to get the right answer, to match the textbook value, to make their data look clean and perfect. This pressure can lead to data manipulation, where students change numbers, delete outliers, or even make up data. This is scientific misconduct. Here's what you need to understand. Science values honesty over perfection. Real experimental data is messy. Real measurements have uncertainty. Real experiments sometimes fail. Your grade should reflect the quality of your experimental process and your honesty, not whether you got the exact textbook value. Let's talk about the actual process of recording measurements. There's a right way and a wrong way to do this. Write down the number immediately after you measure it. Don't trust your memory, don't think you'll remember it, and write it down later. Include all the significant figures that your measuring instrument gives you. If your balance shows 25.47 grams, write 25.47, not 25 or 25.5. Never round your raw data. Keep all the digits during intermediate steps. Only round at the very end when you report your final result. Let me show you why significant figures matter, with a quick example. Let's say you measure a mass of 45.67 grams. This has 4 significant figures. And you measure volume as 16.8 milliliters. This has 3 significant figures. When you calculate density, your calculator gives you 2.71845, and so on. But you can't claim that precision. You round to 3 significant figures, because your least precise measurement had 3, so density equals 2.72 grams per milliliter. The uncertainty in your answer is limited by your least precise measurement. You can't create precision out of thin air by using a calculator. Now let's address a common question. What do you do when your data is really ugly and inconsistent? First, ask yourself, did I follow the procedure correctly? Did I use the instruments properly? Were there any obvious errors? Record exactly what you observed. Then, in your analysis section, discuss possible reasons for the inconsistency. Possible reasons might include systematic errors in your apparatus, random measurement uncertainty, environmental factors like temperature changes, or limitations of your measurement technique. Here's a table showing different types of errors. Random errors cause scatter in your data. Systematic errors cause consistent shifts. Both are part of real experiments. Let me give you another helpful analogy. Think of data collection like making photocopies. When you make a photocopy of a document, you lose some quality. The copy is never quite as sharp as the original. That's like measurement uncertainty. Now imagine you look at the photocopy and think it's not perfect, so you erase parts and rewrite them. You've just made it worse. You've lost the original information. Your first honest measurement is closest to the truth. When you manipulate it, you're moving away from reality, not toward it. Every measurement has uncertainty. This is not a flaw in your experiment. It's a fundamental aspect of science. We express this as result equals value plus or minus uncertainty. This shows the range where the true value likely lies. For example, length equals 15.3 plus or minus 0.2 centimeters. This means the true value is probably between 15.1 and 15.5 centimeters. How do you estimate uncertainty? Generally, it's about half the smallest division on your measuring instrument. If your ruler has millimeter divisions, you can estimate to the nearest half millimeter, so your uncertainty is about plus or minus 0.5 millimeters or 0.05 centimeters. Let me give you a practical checklist for honest, systematic data collection. Follow these steps every time. Step 1. Prepare your data table before you start the experiment. Include columns for all variables, units, and a notes section. Step 2. Record measurements immediately in pen, not pencil. Using ink prevents the temptation to erase and change things. Step 3. Write down all measurements with no exceptions. Even if a value looks wrong, write it down and make a note about why you think it might be wrong. Step 4. Note any unusual observations, problems with equipment, changes in procedure, or anything else that might affect your results. Step 5. Perform all calculations after you finish collecting data. This prevents you from subconsciously adjusting measurements to get the answer you want. Let me tell you about a famous historical example that illustrates the importance of recording all data honestly. Robert Millikan measured the charge of the electron in 1909 using oil drops. His published value was very accurate and won him the Nobel Prize. However, historians who examined his notebooks found that he excluded about half of his data points because they didn't fit his expectations. He got the right answer, but his method was scientifically questionable. He should have included all his data and explained the variations. Modern science demands complete transparency. You must report all your data, not just the data that supports your hypothesis. Once you have honest, complete data, you can perform statistical analysis to understand what it tells you. The mean is the sum of all your measurements divided by the number of measurements. This gives you the average value. Standard deviation measures the spread of your data. It tells you how much your measurements vary from the average. A small standard deviation means consistent data. A large one means scattered data. Let's calculate these for our aluminum density data from earlier, excluding the outlier in trial 4. The mean density is 2.71 plus 2.72 plus 2.71 plus 2.70 divided by 4, which equals 2.71 grams per milliliter. The standard deviation is 0.008 grams per milliliter, which shows our measurements were quite consistent. We report the result as density equals 2.71 plus or minus 0.01 grams per milliliter. The published value for aluminum density is 2.70 grams per milliliter. Our result is very close. The small difference is within our experimental uncertainty. Let me explain why complete, honest data collection matters for the scientific community as a whole. Other scientists need to be able to reproduce your work. If you hide data or manipulate results, they can't verify your findings. Science builds on previous results. If your published data is dishonest, other researchers might waste years pursuing false leads. Your reputation as a scientist depends on your reliability. Scientists who manipulate data lose the trust of the community, and their careers can be destroyed. Medical treatments, engineering designs, and public policy are based on scientific data. Inaccurate data can literally cost lives. Here's one final analogy to help you remember these principles. Think of your experiment like a garden. You plant seeds, water them, and watch what grows. Some plants thrive, some struggle, some might die. A good gardener records what actually grows, including the plants that didn't do well. This information helps them understand what conditions work and what don't. A bad gardener only takes photos of the perfect flowers and pretends the struggling plants don't exist. They learn nothing from their failures. Your experimental data is a record of reality, not a performance. Show what really happened, and you'll learn much more. Let me give you some practical tips you can use in your next lab. Tip 1. Use a lab notebook with numbered pages. This prevents you from tearing out pages you don't like. Tip 2. Write in pen. If you make a mistake, cross it out with a single line so it's still readable. Don't scribble it out or use correction fluid. Tip 3. Date every entry and sign your work. In professional research, this is required for patent applications and legal purposes. Tip 4. If possible, have a lab partner verify your measurements. This catches transcription errors and ensures accuracy. Tip 5. Take photos of your experimental setup and final results with your phone. This visual record can be invaluable when writing your report. Let me summarize the key principles of scientific data collection. Always prepare your data table before you begin the experiment. This keeps you organized and ensures you don't forget any measurements. Record every single measurement immediately after you take it, with all significant figures. Don't trust your memory. Never delete or hide unexpected results. Document them, and note possible explanations for anomalies. Remember that honesty and transparency are more important than getting perfect results that match the textbook. Use statistical analysis like mean and standard deviation to understand what your data is telling you. Always include uncertainty estimates with your final results. This shows you understand the limitations of your measurements. Your scientific integrity starts with how you handle data as a student. These habits will serve you throughout your career, whether you become a scientist or not.